In our last lecture, we started to talk about non-isothermal reactors. And the reason we did that was because we realized that reactions are endothermic and exothermic. And so at the very least, we're either going to require energy from the rest of the system to allow reactions to happen, or we're going to give energy off or give thermal energy off into the system, which will raise the temperature. But those aren't the only sources. In fact, we assumed in the last discussion that this happened, or temperature only rose or fell based on the fact that the reactor was perfectly insulated and adiabatic. But this is not always the case. In fact, sometimes you can think of it that a reactor is just sitting out in a room somewhere, and it's made from, metal, and metals conduct heat. And so, one way to draw this might be that we have our reactor, right? Or we have, I guess I'll draw this as a CSTR. And right, you have flow coming in, you have flow coming out, and the ambient is at some temperature T star, and the reactor wants to operate at some temperature T. And of course, then there's some heat that's going to be transferred between the ambient and the reactor. And sometimes that can have really important implications to a process. And I'll give you one example that I did as a consultant. So I got linked with this microbrewery, and they were having an issue where their blonde ale tasted completely different in the summertime than it did in the wintertime. And the brewer had absolutely no idea what was going on. And so he brought us in and said, hey, if you guys can figure this out, we'll give you some amount of money, right? And so me and a team of undergraduate students did this as a senior design project. And essentially what we found was that in the summertime, it's much, much warmer in the brew house than it is at the wintertime. So in the winter, the heat or the temperature in the reactor, or in the mash tun specifically, was drifting. And the enzyme kinetics in the mash tun were totally different than in the winter and the summertime. And for a biological reaction like that, temperature is very, very important, because those enzymes are only active over very small windows most of the time, maybe plus or minus 10 degrees. And so we were able to essentially tell them that they should look for a second configuration for the mash tun, which of course is where the barley is introduced to hot water, right? And you remove the soluble starches, then the enzymes break those down into sugars, which then you're going to ferment later. And we suggested to them that they should try to control the rate that heat is either lost or added to the reactor, or really to maintain it at a known temperature by jacketing the reactor. And so this is another configuration that you could think of as well. So one way is that you can just have sort of passive heat transfer between the ambient, like I show in this image here, or the thing that we can do instead is we can say that we'll design a reactor now that we're going to flow a secondary fluid through this jacket. And so you can have a fluid outlet, a fluid inlet, and that act of flowing is going to either add heat or remove heat to the system, because now the heat transfer occurs between the reactor and the jacket. Now, of course, we know in real life that the fluid's going to come in at some temperature, right, that is like T star in and T star out. And the temperature is going to change here. Now, one of the things that we could do, and something that we'll do maybe in this first part of our class today, is let's just make an assumption that, say, there's really, really high flow rate. And so the difference in the temperature is negligible. And so the jacket now is just at some approximately constant value that we're going to call T star, and our reactor is still operating at some time T. And so what we need to do is to determine how a situation like this, where we have heat transfer between the reactor and the environment, is going to impact our energy balance that we derived in lecture 12. And of course, our steady state open system energy balance was simply that Q plus W plus the sum of the enthalpy that is entering from flow minus the sum of the enthalpy that is leaving because of flow is equal to 0, right? And those are both the sum over I. And just like we did in the previous lecture, we can say that we're most likely not going to do any work. So the only difference here is that we have to figure out how to describe the heat transfer that is occurring between the system and or the reactor and the jacket. And there's a very straightforward way to do this in that in ECHE 321, you guys have a relatively simple expression for this, that the heat transfer is just equal to the heat transfer coefficient times the difference in the temperature. And of course here, we're going to define the difference in the temperature as T star minus T for our reactor. And what we would expect then, of course, is that if T star is greater than T, heat should flow in, so the sign would be positive, and it is. And if the temperature of the reactor is higher than the temperature of the fluid in the jacket, that the sign of Q would be negative, which is exactly what it is here. All right. So let's look at how this influences our derivation that we had last time. So now we have this UA times T star minus T plus the sum of the enthalpy entering, right, at the initial temperature from flow minus the enthalpy that's leaving at the exit temperature from flow is equal to 0. And remember, we made a substitution here in lecture 12 where Fi was equal to Fi0 minus Fa0 times the stoichiometry of I over A times the conversion, and that came from our mass balances. And so we ended up then simplifying the right two-hand terms here, and we got UA times T star minus T plus the sum of HI at T0 Fi0 minus the sum of HI of T times Fi0 minus Fa0 times the ratio of the stoichiometries times the conversion. And then we group terms. So if you remember last time, we grouped this term with that term. And we ended up with an expression that was well, I guess we didn't have the UA part, but on the right-hand side here, we ended up with the sum of Fi0 times the initial enthalpy minus the final enthalpy plus Fa0x times the sum of the enthalpies at the final temperature times the ratio of the stoichiometries. And I'm sorry if I'm going a little bit fast, but all of this we did last time. And so I don't want to spend a significant amount of time rehashing something that we already did. But this, we said last time, is simply minus delta H, right? Which was minus the integral of Cp dt from T0 to T. And we also said correctly that this sum is just minus delta H of reaction per mole of A, okay? And we get a really nice expression if we make that substitution, right? So we have then UA times T star minus T minus the sum of Fi0 times the integral of Cpi dt from T0 to T minus Fa0x times delta H of reaction at our final temperature is equal to 0. And then we made one more change, is that we recognize that Fi0 over Fa0 equals theta I, or that Fi0 equals Fa0 times theta, right? And we defined this a couple of lectures ago. And so we can insert that into here as well. We get T star minus T minus Fa0 times the sum of theta I times the integral of Cpi dt from T0 to T minus Fa0x times delta H of reaction is equal to 0. And if the heat capacity is approximately equal to a constant, which it doesn't have to be, we could do the same integral using the delta CP method or using the NIST chemistry webbook that we discussed in the last lecture. But if the heat capacity is approximately constant, this becomes UA times T star minus T minus FA0 times the sum of theta I CPI times T minus T0 minus FA0x times delta H of reaction is equal to 0. Now, I would just solve this computationally, right? If I had a problem, I would just call this done. I would say, here's the result of our energy balance for a flow reactor at steady state that is jacketed, or where there's heat transfer from the reactor temperature to some constant temperature on the outside of the reactor. However, your book, if you go, when you study, they actually solve explicitly for the conversion. So they use this to actually calculate the conversion, and they get that the conversion that's predicted from the energy balance, which they call XEB, is then equal to UA times T minus T star, right? Again, where T star is the jacket temperature, over FA0 plus the sum of theta I CPI times T minus the initial temperature divided by minus delta H of reaction at the final temperature. So the book does that. They explicitly solve for this thing that they call the conversion from the energy balance. The other thing that we also could do is solve for the temperature explicitly, because if you remember last time, we ended up with an expression that T equaled T0 plus essentially the reaction term. And so if you want something that looks very, very similar to that, you can solve for that. And you do that by foiling this expression out to try to get those terms that are simply related to our reactor temperature at the end. And if we do that, it's a little bit of a pain, but we can do that relatively simply. This just becomes UA times T star minus UA times T minus FA0 times the sum of theta I CPI times T plus FA0 times the sum of theta I CPI times T0 minus FA0 times X times delta H of reaction is equal to 0. And from there, we're going to just, we're going to just group the temperature terms. And so we find that the temperature times UA plus FA0 times the sum of theta I CPI equals minus FA0x times delta H of reaction plus UA times T star plus FA0 times the sum of theta I CPI times T0. And so we can get an expression that's explicit in the temperature. So that's just minus FA0x times delta H of reaction divided by UA plus FA0 times the sum of theta I CPI plus UA times T star divided by UA plus FA0 times the sum of theta I CPI plus FA0 times the sum of theta I CPI T0 divided by UA plus FA0 times the sum of theta I CPI. Okay, so hopefully you see this expression and go, oh, that's why he told us he'd much rather solve that equation. Okay, I really would. I like setting equations equal to 0 and just solving things that are linear and they look very, very straightforward to do. Now, if you prefer this one or even this one, that's fine. One of the things when I do a bunch of math and I'm really not certain whether this is right or not, I try to think of a test where I can figure out if I'm right. And the one that I came up with here was this expression that we derived should break down to our original expression when there's no heat transfer. And when is there no heat transfer? When UA is equal to 0. So when UA is equal to 0, right, that goes away. This whole term would go away, and this whole term should go away. So when that happens, this will cancel with this, and you're just left with T0. And so we are then left with T. So when UA equals 0, then T equals T0 minus FA0X times delta H of reaction over FA0 times the sum of theta I CPI. And of course, those FA0s, right, are going to cancel. And that's exactly the expression, or that is exactly the expression that we derived last time. So this works, that the solution that we derived just now breaks down into the thing that we did last time when there's no heat transfer taken into consideration. So that's a good thing, okay? It's kind of like your litmus test for if your solution sort of passes, okay? So what have we really done so far? We've developed a relationship, or solved the energy balance to develop a relationship between the jacket temperature, our reactor temperature, and conversion, which we needed last time, right? Because now when the temperature changes and the compositions change, the number of mole balances we need is essentially N species, however species are present in the reactor. And now for the temperature, we need an energy balance. So in our previous example, where it was adiabatic and this term wasn't there, we could use that solution. And in this case, where there is a jacket, we will use that version of the energy balance to solve problems, okay? Now, before we do that, before we go about solving a problem and talking a little bit more about jacketed reactors, I want to give you guys the chance to ask a question if you have one after all that math.
I had a question about the temperature being explicit in that equation, because you have to know the temperature to know delta H of reaction. So I didn't know how you would approach that.
Yeah, that's a really nice question. So it's another reason why I like to solve this version of the equation. So this comes out nicely, or this comes out nicely when you already know this ahead of time, or you can assume that that's approximately constant. And there are some reactions where that's okay. When you don't know that, you're going to end up solving these either using MATLAB or Excel or something like that. And you will set up a spreadsheet where you're solving for the heats of formation for all of the products and reactants at the initial temperature and the final temperature. And then you will have that temperature be something that is adjusted in the solver, whether that's in Excel or in MATLAB. So that's a great question. And it's another reason why it's much easier to solve something like this, because then you have supporting equations that calculate the heats of formation as a function of the temperature. So I think that's a really good question. It's really one of the fundamental reasons why I don't like this, because you have to know that beforehand for this to come out, for it to come out that nicely. So anyway, I think that's a great question. And it's the same thing with this, right? You'd have to essentially assume that that was equal to a constant in some temperature range, or have a simple functional form for the delta H of reaction over some temperature range. So yeah, that's a really great question. Does that help, at least with how I think about it?
Yes, it does.
All right, great. Okay, any other questions? That was a good one. All right, so if not, let's look at the same problem that we did in lecture 12, except we have one change. So we still have the exact same expression for the rate constant. We have the same reaction where water and acetic anhydride are reacting through this pseudo first order elementary reaction. We have the same starting concentration that we did last time, 0.216 molar. And the reactor is still operating at 15 degrees C. We know the volumetric flow rate. We know the reactor is 150 liters. So the new information that we're given is that the reactor is a 1/4 inch thick jacketed stainless steel reactor with coolant rapidly flowing through the jacket at 15 degrees C. So now we're going to have to use this information to figure out how much heat transfer is happening and then determine the final reactor temperature. Okay, so the exact same system as last time, but now we're in a jacketed reactor. So we derived our expression for the mole balance. So here we're looking at the concentration of A, and we're looking at the energy balance. So if you remember last time, our mole balance simplified relatively nicely because we have in minus out plus generation minus consumption is equal to accumulation, which is 0 for our steady state reactor. And so this is just Ca0 times the volumetric flow rate. It's liquid, so the volumetric flow rate is equal to a constant. So that's also just Ca times V minus K1 times Ca times V was equal to 0. And we simplified this by just combining terms. Then minus K1 times the volume, which we're given here, times our expression for K1. And that was 0.00736 T minus 2.040. And the unit there was inverse minutes is equal to 0. And nothing changes here. So our mass balance is exactly the same as it was in lecture 12. We haven't done anything to flow rates. We haven't done anything to the volume. So this should be fine. So the thing that's new is our energy balance. And we're going to use UA times T star minus T minus FA0 times the sum of theta I CPI times T minus T0 minus FA0X times delta H of reaction is equal to 0. And I like going back to this form when I can, because depending on our system, we might be able to simplify it. So remember in lecture last time, we made a couple of simplifications here. The first one was that the sum of theta I CPI, we significantly shortened, right? That essentially was just equal to the flow rate over the flow rate of A, or the molar flow rate over the molar flow rate of A, times the heat capacity. And we know that the conversion is defined as FA0 minus FA over FA0. And we can make those substitutions. So we'll put this back in here, just like we did last time. And this expression for the conversion is going to go there. Sorry for all the loopy arrows. And when we do that, this simplifies pretty well. UA times T star minus T minus our molar flow rate times our heat capacity times T minus T0 minus FA0 minus FA times delta H of reaction times the conversion, of course. Oh, sorry, we already substituted the conversion, is equal to 0. Sorry about that. And then we know that, or we said that our F water was equal to the volumetric flow rate times the density over the molecular weight. We did that in lecture 12 as well. And we also know that the heat capacity, right, of our system is essentially, was given to us in the wrong units. And so that was also Cp times the molecular weight. And we can make those substitutions here, and we end up with the following expression. So UA times T star minus T minus the molar, volumetric flow rate times the density times our heat capacity in the units we have times T minus T0 minus the volumetric flow rate times CA0 minus CA times delta H of reaction is equal to 0. And this is our second reaction, or our second equation that we can solve, right? So that's equation 1, that's equation 2. Now, what are we missing here that we actually have to figure out? So we're treating this equation like presently the concentration of A and the temperature are the only unknowns. But what else haven't we figured out yet?
UA?
Yeah, we don't have UA. That's correct. So how do we find it? Right? How do we determine UA? Well, this is where we need information about the vessel. So we need to know the size, we need to know the shape, and we need to know what it's made from, right? And from there, we actually can figure this out. And let's do that using relationships that you guys already have seen from heat transfer. So we know that U, or a relationship for U, is 1 over U is equal to 1 over the thing we call H1 plus the length over K. And actually, I'm almost out of Ks, but I'm going to use this like little kappa maybe. I don't want to confuse that with our K1, 1 over H2. And if you remember, H1 and H2 are the convective heat transfer coefficients for a fluid, or for the fluids on either side of the walls. Now, oftentimes we assume that H1 and H2 are very large. And when that's the case, this simplifies very nicely, and we just get that U is equal to K over the length, where K is basically the heat transfer coefficient, and L is the thickness that we're looking at. Now, we're told in the problem that our reactor is made from stainless steel. And so you can actually look up the heat transfer coefficient for stainless steel, which I did, and it's 25 watts per meter Kelvin. And we were told in the problem statement that our reactor thickness is 1/4 of an inch. And so that is 6.35 times 10 to the minus 3 meters. And so that gives us a U of 3937 watts per meter squared Kelvin. Okay, so now we have U. The next thing that we need is A. And so we're going to need to make some kind of assumption about the shape of the vessel. So the thing that we're going to assume here is that we did a problem on a CSTR, right? So, we have some CSTR, and it's going to have, some diameter, and it's going to have some height. And here we're just going to assume that they're the same, right? So our aspect ratio is 1. So we're going to say that D is equal to H, and we're just going to call that capital L. So we don't have to track D's and H's around. So we know that the volume of the cylinder here, right, is just equal to pi r squared times H, right? Which of course is pi times D squared H over 4. And remember that D and H is equal to each other. So that just becomes equal to pi over 4 times this dimension L cubed. And we know the volume of our reactor in this case, right? It's 150 liters, which is 0.15 cubic meters. So we can calculate the length from 4 times the volume over pi to the 1/3. And so that's just 4 times 0.15 cubic meters divided by pi to the 1/3. And so that dimension is 0.576 meters, okay, for that reactor. And now we have to find the area. And we know that the area for this has 2 components to it. The first one is the outside, and the second one is the face at the top and the face that's on the bottom. So to calculate the area, well, the area around the reactor is just pi times the diameter times the height. And then it's plus 2 times pi d squared over 4. And of course, given the dimensions that we know, that's just pi times L squared plus pi over 2 times L squared, right? Or 3/2 pi L squared. And so doing that, we have an area of 1.56 square meters, right? Just putting our value in here. And now we have the value for UA given the physical dimensions of our reactor. So that's 6153 watts per meter squared Kelvin, okay? And using that, we now have 2 equations and 2 unknowns, right? We have now CA and T are our equations for these 2, and we know everything else about the system, right? We know the initial concentration, the volumetric flow rate, we know K1, and we know the reactor volume, okay? And so we can solve those 2 equations. And when we do that, we were going to find, right, we were asked for what the temperature is. So our temperature is equal to 295.1 Kelvin, okay? And if you go back to what we did last time, that is around 2.5 degrees Kelvin lower than last time. Now, of course, this brings up a question. Does that matter? Maybe. So I gave an example at the beginning of our lecture today about the brewery where we saw, an 8-degree Fahrenheit drift. And well, our product at the end, and that's the thing as a chemical engineer we care about, right? Taking raw materials through a process to make a product. In the brewery, fortunately, we could consume it afterwards. You can't always do that. It's not always recommended. But in that process, that's a huge problem. And so oftentimes, what you're trying to do in a process isn't really just predicting what temperature your process will be at the end. That does happen, especially for things like combustion or when you're using combustion to provide heat for a reactor. But it also leads to other questions that we could ask that maybe make even a little bit more sense. So in this process, what temperature, right, given our reactor, would make the process isothermal? Because certainly in the brewery, that's what we were interested in at the end, was what temperature makes the process isothermal. And the nice thing about that is we can get that relatively easily. So if you remember our energy balance from above, right? So this reaction here. Well, when the reactor is isothermal, that whole term goes to 0. So this is going to be relatively straightforward. I mean, we can take UA times T star minus T0 minus the volumetric flow rate times the density times the heat capacity times T minus T0 minus the volumetric flow rate times CA0 minus CA times delta H of reaction, right? That's equal to 0. And I just said, if we want to figure out how to make the process isothermal, that just means that T minus T0 is equal to 0. Well, that simplifies this to just UA times T star minus T0 equals the volumetric flow rate times CA0 minus CA times delta H of reaction, right, at that temperature. So then T star minus T0 equals the volumetric flow rate times CA0 minus CA times delta H of reaction over UA, which means that T star equals T0 plus the volumetric flow rate times CA0 minus CA times delta H of reaction over UA. And if we look at this expression, when the reaction is exothermic, then T star has to be less than T0, which makes sense because then you have to take, you have to be able to take heat from the reactor. And when delta H is positive, then T star has to be greater than T0 in order to allow heat to transfer from the jacket into the reactor. Okay, so that makes sense. Okay, so this leads me to our next question. How can we improve heat transfer in the system? So oftentimes, if we want to have a jacketed reactor, that's really important, right? Having heat transfer be as fast as it can be, but you don't want the reactor to be prohibitively expensive. So what's a couple of ways that we could improve the rate of heat transfer in a vessel like this one?
I'm not really sure if we're even like considering resistance, but my first instinct would be to say like reduce resistance somehow.
So it's funny that you use the word resistance. That's really what this is, right? That's really a resistance. And this is like, if you were to think about this as a wire, this would be equivalent to the resistivity, right? This thermal coefficient. So this is a lot like that concept of a resistor. So reducing the resistance to heat transfer, I think, is a very good one. And so there's two ways to do that. One is to increase K, right? That's one way to do it. So let's say that we went from stainless steel, which had a heat transfer coefficient of 25, to aluminum. Aluminum is 205 watts per meter Kelvin. So that's one really good way to do that. Another way is to make the reactor thinner. Now, sometimes you can't get away with that because you have some minimum rigidity that's required. Another thing that we could do is to change the shape, right? So this area term, we assumed that it was a cylinder, right? And we assumed an aspect ratio. So you could change the aspect ratio. You also could make it spherical instead of cylindrical. And really what you're trying to do there is to increase the surface area to volume ratio. There are some things where you get to aspect ratios that aren't practical, but it would increase heat transfer. And spherical reactors, if you were to Google this, you can find spherical bottom CSTRs. And they're trying to do this. They're trying to maximize heat transfer. They're also trying to do things with mixing as well. And spherical shapes are great for things like this because they have the largest surface area to volume ratio. But sometimes the implementation is difficult because you have unused space and other things. But I think that was an interesting way to think about it in terms of the resistance. So that was very nice. Okay. All right. Any questions before we do sort of the last module for today? Okay, so if not, let's extend this to a PFR, okay? So let's look at a jacketed plug flow reactor, okay? So we've drawn a PFR simply as a tube here, right? Of course, we have flow in, we have flow out. If we draw the jacket, so, I'll do that here. So I'll just draw the jacket along this length, right? And we also have flow in, right? And we have heat transfer that's occurring between the reactor and the jacket. And we'll also make the same assumption here that the temperature of the jacket is approximately equal to a constant, okay? And that'll help make our life a little bit easier. One of the things to note here is that our energy balance only assumed that we had a flow reactor operating at steady state. So this equation that Q plus W plus the sum of HI Fi0 minus the sum of HI times Fi is equal to 0, that still holds. So we don't have to change that at all. But there are some interesting things here where if we know that there's no work being done and Q is still UA times T star minus T, right? So this is plus HI T0 Fi0 minus HI of T times Fi. We know that our mole balance for a plug flow reactor is dFi dV is equal to Ri. And that means that we're going to need to figure out how the temperature is changing as well as we progress through the reactor. So we also want to get a derivative that looks like something like dt dV is equal to some stuff. But where is volume in this expression? Does anybody see where the volume is?
In the area?
Exactly. And we just looked at that even in our previous example, right? That we used the reactor volume to calculate the area. So that's correct. So what's normally done here is that for different shapes, we define a shape factor that is a lowercase a, and that's just equal to or defined as delta A over delta V. Now for a cylinder, A is just equal to 4 over the diameter. And you could use the equations we used a minute ago to determine that. Now we're not going to use 4 over D for anything right now, but I just want you to know that. So now we can actually insert this into there. And if we do that, we know that UA times T star minus T times delta V is equal to the sum of HI at T0 Fi0 minus the sum of HI T Fi, right? Oops, sorry, not equals. That was plus and minus, sorry. So we have a delta here. The other delta that we're going to find is in this. And this is just equal to minus the sum of delta HI times Fi. Right? These two expressions are just how the product of the enthalpy and the flow rate change from the beginning state to the end state. And so that means that UA times T star minus T times delta V minus the sum of delta HI Fi is equal to 0. And so now we can take the limit as the volume goes to 0. And if we do that, UA times T star minus T dV minus the sum of dHI Fi is equal to 0, right? The deltas just become differentials. And we can use the chain rule for this. And when we do that, that's UA times T star minus T dV minus the sum, or I guess the sum of HI dFi minus the sum of Fi dHi is equal to 0. And I'm going to divide through by dV. And you end up with UA times T star minus T minus the sum of HI dFi dV minus the sum of Fi dHi dV is equal to 0. And we're almost there because we actually already know this and this. So remember, for a PFR, dFi dV is just equal to Ri. So we also know the relationship between Ri and Ra, right? So Ri over the stoichiometric coefficient for I is equal to Ra over Va. So really, this Ri just equals Ra times the ratio of the stoichiometric coefficients in our reaction. So the first term here becomes, or the second term becomes, just minus the sum of HI times RA VI over VA, right? And the second term here, which I'll use a different color, well, we know that the enthalpy is just that dH is Cp dt, right? So dH is just Cp dt. So dH dV just equals Cp times dt dV. And so the third term just becomes minus the sum of Cp dt dV times Fi, and that's equal to 0. And we can rearrange this and find that the sum of Cp I times Fi times dt dV equals Ra, and remember that the sum of Hi times the stoichiometric coefficients is just delta H of reaction. And so that becomes Ra times delta H of reaction plus UA times T star minus T. And so finally, we have an expression that dt dV is equal to the rate of A times delta H of reaction at that temperature plus UA times T star minus T divided by the sum of CPI times Fi. So that is our expression for the energy balance, or the solution of the energy balance for a PFR, right? So this is our energy balance. We also need our mass balances, right? That dFi dV is equal to Ri, right? These are our mass balances. And when we come across problems like this, there's really only one way that I think of solving them, and that is to use software. Either Excel with Euler's method, or MATLAB, Mathematica, MathCAD, Polymath, whatever you guys like to use. But of course, we focused a lot in our semester on using Euler's method in Excel because it's pretty easy to implement. And the reason that I say that is because this is basically the easiest problem that we could have solved. And look at the complexity, right? And how they are linked to each other. So when we solve problems like this throughout the semester, we are going to look to a program to help us do that.